Welcome everyone to another episode of Mechanisms and Mentorship with my guest Tanner Green, your host Rafael Testai. So let's dive right in. What problem were you trying to solve? What's the big picture?
Great question, Raf. So the big problem here from the customer was they said they needed to clamp on small diameter wire at various diameters, but very small, and do it at a specific depth. That was the main problem, is how do we do that? There's other little things that came in, but really that's what they wanted to do.
So there's a wire, presumably from a medical device, correct?
That's correct, yeah.
And we need to clamp it at different diameters.
Yeah, so slightly different diameters. We had really, really small wire samples. And so we had about, let's say, 5 different diameters that we were trying to clamp on, all really small. But then the other part is they need to be able to clamp those at a very specific length along the wire. So that was another part of this that we needed to achieve.
So when we say specific diameters, I guess it matters how much force you apply, because if you do it too much, you may break the medical device or the wire?
Yeah, that's right. So there's kind of a balance here. This is a clamp. The idea is that this is going to be used for like a tensile test, right, which is a very common test in engineering validation. And so you want to make sure you don't damage the sample when you're pulling it, because any sort of damage or compression to the sample could actually induce a failure at that cross section. So we wanted to make sure we clamped on it with enough force that it doesn't slip, but not too much that it's damaging the sample.
Perfect. Well, if you want to show us a little bit about how you went about solving this problem, and again, big picture, because none of us have seen this CAD file before, so we don't even know what we're looking at yet.
Sure. Yeah, so big picture, this is actually, I'll call it 2 different fixtures together, or 2 different mechanisms. And we started with the first, which is just what I'll call the clamp, right? We needed the clamp to clamp on the samples. And we added the second fixture, which is what I'll call the nest. That came later as a supplement to the clamp after we started to realize and get into some different stuff, which I'm sure we'll talk about a little bit. But we realized we needed that to make it user-friendly so the operator could actually end up using this. So if you're looking at this, really on the screen, what you'll see is the 2 different fixtures. So you've got the nest, which is this blue looking plate, and the handles, these paddles. There's also a gauge here. I mentioned the depth, that, you know, the length along the wire that needed to be specific.
If you want to go ahead and zoom into that and bring it to the front of the screen so people can see there's numbers engraved in it, right?
You bet. So we had numbers engraved on this. This was just to be marked at certain lengths, and this is just really an operator aid. This was more just a desire by the customer. They wanted this so it was very quick and easy for a operator an operator to reference against this to know the exact length that they needed. This is also something that was kind of historically in their process already, so they wanted to keep this. But we also, if you look at this, you can see here on the clamp itself, we actually added markings here as well. These are also engraved. This is just matched up to the markings. It's just a ruled jaw, and that allows us the operator to see exactly where the depth is in this particular case. So maybe a little bit of detail on this. So in general, the high level of what this does, like I said, the clamp is supposed to clamp on the wires, and really it's 2 parts. So if I
Pause real quick. Let me imagine this. Sorry to cut you off, but
you bet.
There should be a wire that we're hiding in the model because we don't want to show the customer product, but we can show what we designed. So imagine a wire going through here.
That's right. So the wire's just coming right out through that. This part right here, it would be clamped in between those jaws.
So these jaws are clamping the wire, okay, as you pull on the yellow. Is that right? Is that how it works?
Sort of. So this is where the mechanism really gets interesting, right? So what you can see here, I'm going to show a different state. So right now this shows the clamp as closed, right? And if you can picture this, what happens is the operator would actually push down on one of these 2 levers, these handles right here, or paddles, right? And then within that, what would happen is we would take this clamp, and the clamp becomes opened as they push down, right? So if I'm going to just go ahead and change the configuration here. Oh, and we'll get to this, but the mates are one of the things that was a challenge with this. But really, so what you see here is we have now the clamp opened, right? But there's a key feature that is important to remember.
Could you click on the clamp face so we know what we're looking at when you say it's open?
So right here, these are what I'll call the clamp jaws, right? These are 2 different jaws. those are the parts that actually clamp onto the sample in this
Perfect.
case,
I can see it. Thank you for that.
Yeah, you bet. And so what's happening here is when I push down on these two levers on the two sides, right? These are what we'll call the paddles or levers. This entire block right here actually slides down, which I'm not going to be able to show it right now, but let me change this state. So if I push that to an open state, what actually happens is it moves downward in the direction we're looking at it, right? Actuates against what I'll call the clamp body, and then allows these clamp jaws to open up. Now what's really particular about this is these jaws only move, relative to how we're clamping it, only move in one direction. So it's kind of a complex movement, but it'll result in just a X translation of the jaws, right? And that's critical because in this particular case we need a specific depth of insertion, and that's why. When the jaws are moving in two directions, if it's moving in an XY vector, it actually becomes really, really difficult to get the precise placement that you need. So in this case, by moving in just one direction, it opens left and right, sample is inserted, closes left and right.
Very cool. Now, zoom out just slightly. I want to ask you, how does the technician push these down? How does that work?
So what in a standard operating procedure, they would actually they would pull their sample. If they desired, they would reference it against the gauge here on the right, right? And then from there, with one hand, they would reach over and grab or push down, literally just push directly down onto the tabletop. So we're looking at it as if we're from above, right? And so they would literally just push that paddle down. The paddle rotates about a pivot back here at the back, and then there's a set of 4-bar actions that allow this slider to move. And when they do that, so one hand's pushing down on the paddles, the other hand's holding the sample, and it's just reaching right in. And then with the hand that's pushing the paddles, they release it, and the clamp closes right onto the wire.
That's a beautiful explanation. By the way, this is the first try. We just did this on the go, so that's fantastic.
That's right.
Now, let me ask you, what was your inspiration to come up with this solution? Because most of the time from these episodes that we're doing, mechanisms and mentorship, the engineers tend to look at existing solutions and use that as inspiration. So could you walk us through?
Yeah, for sure. So just like you said, this really was something that was inspired by stuff that exists already. In a general design process, we would look at this and say, I mean, there's a couple things you gotta do. You gotta look at what is it the customer trying to achieve, right? At the end of the day, what is it that they need? There's a lot of different ways people might call this. We might call it functional requirements. We might call it customer needs. There's a lot of different things like that. But once you know what job the customer's trying to do or what they're trying to achieve, from there, my personal preference is to go look and see who's already solved that problem, who's already done that job, right? So yeah, we actually thought for this particular project, we thought we were going to be able to use mostly off-the-shelf stuff. We thought this might be just an integration project where we would just select different parts that we needed to meet the requirements, and then we just assemble it together and it would work.
So one moment, I want to highlight that. So that seems to be an industry term, integration. So you grab off-the-shelf components, a mind that understands the problem, puts it all together, and there's minimal custom parts.
Correct.
Right?
Yeah,
okay.
That's exactly right. Yeah, integration would just be I'm taking different bits and pieces and I'm integrating it together, putting it together for one solution.
So it seems like you thought that was the way that we were going to go, but it wasn't, was it?
That's right.
Okay.
That's right. Well, and you know, we didn't know that up front. Had we known that we were going to go down this route, we might have approached it differently. But we didn't know. We didn't know that was going to be an issue. What we knew was the customer had an existing solution in place that they weren't happy with, right? And as we started looking at the different constraints or requirements that the customer had, we kept asking ourselves the question, why aren't they using something off the shelf, right? Like, why isn't this already being used? Because this seems like it would be so straightforward. We should just be able to use something off the shelf.
By any chance, could you reference maybe on Google Images what you thought was the solution that already existed?
Well,
so what Tanner's going to show us is a potential solution that he thought was feasible to solve the customer's problems, right?
Yeah, that's right. Okay, so here's an example of an off-the-shelf clamp, right? So what you can see here, there's a couple of different things to this. You have the main body, and then over here on the right side of the clamp, you've got this twisting actuator, right? This is going to be basically like a screw, and these jaws are going to be actuated by that screw mechanism, right? I tighten it or I loosen it depending on which way I rotate it. You can also see traces here. If you look down here, this little slot, if you're looking on the screen, down here, there's slots on either side. That's actually indicative of the motion that is going to go, right? So in this particular case, you can see those slots run kind of up and down on a vertical XY component, right, relative to the body.
That's a deal breaker, isn't it?
Well, so we didn't know. We didn't know if it was or not. We learned that it was, right? So what we found here is this is an example of something where this is a very simple clamp to make. You could buy this right off the shelf, right? And we could just integrate it. And so it would also have, up on top, it would have an interface where you could actually attach it to whatever test structure you're using. So there's a lot of common test jigs or what do they call it? Test stands out there, right? So this seemed like it was just a slam dunk. Like this should be really easy to do, right? There's also one other thing I'm going to point out here. You see these jaws, right? The jaw pattern. I mentioned the wire was really small, right? The wire was so small that these jaws would basically just cut it. Like it would literally just cut it when you would clamp on it. So you couldn't really clamp on it because the wire was so small. It would just break from the clamp.
Would it be the teeth of the clamp also?
The teeth,
okay.
Yeah. It's like that kind of serrated edge. That's what it would look like, right? So that's really good with certain types of samples, but the particular kind of material we were using and the size of the nature of it, it just wasn't working, right? So we actually bought several of these to test on. Different brands, different manufacturers, different clamp types, and ran a bunch of tests. And the deal breakers we found were, because of how small the wire was, it would either damage the wire, so we couldn't actually do a full test on it. The wire would slip, we couldn't place it right, or there wasn't enough depth on the clamp to insert it. So for example, I think if you look at the model, if we looked back at the model here, you can see that the depth here goes up to about 2 inches, right? You can see that on the model, right? And so what we were concerned about was we need to be able to insert it at least 2 inches. But looking at this particular clamp, it wasn't 2 inches deep, right? So we would have to modify an existing off-the-shelf one to make it work, right? And so there were so many different parts and features and things that we were running into. We realized an off-the-shelf really just isn't going to cut it.
I was laughing a little bit when you were explaining, because what if a customer pays you a big purchase order to come up with a solution, but really the solution already exists?
Yeah.
So you just buy the solution, you hand it to the customer, here you go.
Yeah, that's a tough thing. That gets into the relationship with the customer, right? I mean, obviously, if you're able to buy something off the shelf, depending on your agreement and how you're doing it, maybe it's going to cost them less too, right? And there's a lot of reasons people may not be using it off the shelf. And that, for us, we took a step back, and after we started going through this exercise of, can we use something that's off the shelf? We got to a point where we wanted to really understand, so why aren't you guys using something off the shelf to the customer, right? So we had conversations like that. We really wanted to know, hey, and we were really forthright with him. Hey, this is what we're thinking. This is the direction we want to head. Are you okay with this? We might be able to find something that's off the shelf. They were totally fine with that. But yeah, you gotta treat your customers right? Make sure you're taking good care of them and understand what their needs are. So in this case, yeah, once we were forthright with that and really understanding, this is what we're seeing. These are the tests we're running. This is what we're experiencing. It became clear that no, you know what, we actually need to take a different direction and go down a totally custom route.
In your entire career as a mechanical engineer, have you ever had a customer that was willing to do a decent sum of a purchase order, and then you turn around and you actually do find that there is a solution off the shelf that's significantly less expensive?
Yeah, good question. I'm sure I could think of a specific example. There's not any that's come into my mind. A lot of my career has been spent in very custom, fixtures. So this is probably the closest to that. One of those where we thought, yeah, we might be able to do this, and honestly, we thought we were going to be able to deliver at a very low cost because we wouldn't have to put a lot of design work in, right? It's just testing.
So when you looked at how the mechanism works, did you actually have to disassemble it and study the mechanisms on the inside, or from the outside you could tell how it worked?
Great question. So, it kind of varies. There are more complex mechanisms than others. For this particular one, we ended up taking a couple of these, looking at them, tearing them apart, trying to understand how they worked. And really, they're simple. These are, I mean, clamps are some of the most simple mechanisms out there, right? I think sometimes we take them for granted just because they are. There's so many things that we use as a clamp all the time, right? Something with a screw mechanism, something with just a spring mechanism. So
This is the clamp right here for the microphones.
That's right.
Clamped onto the table.
that's right.
Yeah.
So clamps are everywhere, right? But yeah, this particular type of clamp, we wanted to understand how it worked, and I think more so, we wanted to understand why it wasn't working, right? So buying these off-the-shelf solutions, we wanted to understand why isn't this working? Like our test results, we knew the requirements, like I said, right? But why are we not getting the kind of results we want to get? And so for us, it was taking things apart and understanding and dissecting, really why doesn't that work, right? And sometimes
Understood.
that's just as good as knowing how it works, right? It's just why doesn't it work?
All right, so moving on to a more general question, which is how does a senior designer like yourself approach a design problem? Do you have a specific process you follow? And if you could just break that down for us.
Yeah, sure. So, I'll talk a little bit about my own design process, kind of the way my thought process works. Here's what I think about when I think about design thinking. So, a lot of it starts before you're ever putting something to paper, right? Like pen to paper or before you're even building something. I think about it in terms of first you got to understand what you're trying to do, right? At the end of the day, that's like the reason we design things is to do something, right? Like that's why we design it. So understanding the customer needs, in design thinking they call it empathize, right? You really want to understand what's the challenge the customer's facing. What job are they trying to do? That's a term, the job to be done theory, right? That's a term coined by one of the Harvard business professors. Anyway, thinking about empathizing with the customer, once you know what they're trying to do, from there, I think the art part of engineering actually starts at defining, right? So if you think about this in terms of, for me, the way I look at it is, it's really easy to just over-constrain something. It's a lot harder to kind of take a step back and see what constraints you can remove and the system still not break, right? So for me, I like to try to starting at that base challenge and then kind of a blank slate in front of you, going into it and saying, what can I use or how can I define this? We talked about it needs to be a clamp. In this particular project, we've been talking about this mechanism. Does it have to be a clamp that is two jaws, or can it actually be a roller and something else, like a cam roller, right? There's a lot of different ways you could potentially define that. So the art, to me, is starting to define what constraints exist, and then sticking to those constraints. So once you've figured out what the customer needs, and you start to apply your own constraints.
I have to say something.
Yeah.
What if after you think it through, you decide that, you know what, actually some of these constraints don't have to be there, and you mentioned the roller, but then the customer is so set on being a clamp. How do you talk to them about it?
No, it's a great question. So that actually, honestly, I think that is the harder part, right? Is it's a lot easier to just think about the constraints and then define them however you want. It's a lot harder to get people to buy off on it, right? So
sales training.
That's right.
Yeah.
I think the way, well, I'll tell you the way I go about it. The way I go about it is we try to really focus just on the problem and then show how a specific path or specific constraints impact downstream, right? Downstream in the design process or downstream in the implementation or whatever it is. We want to make sure the customer understands that. To me, at the end of the day, this is design as a form of communication, right? It's one of the ways we use to communicate something. And so, really it needs to be just how do we take what you're saying you want and apply it, and what's the impact? Does it over-constrain something or under-constrain something? Do we need to add more or take away, right?
I guess help the customer see that there's more ways to solve a problem, but just focus on solving their problem, and hopefully they can share the view.
Yeah, and I'll be honest, there are times you're going to run into customers where it doesn't matter what you say, they're going to tell you this is what I want, right? And they will be the ones that define the constraints. And there are times like that you sometimes just have to say, okay, that's what we'll do.
What if a customer is like their worst enemy?
Oh man, it happens. It does. I can think of there was an experience I had at a past company where, the things that the customer was telling us they wanted, honestly, it was making things so much more difficult, right? And I think there's two sides to this. One is you implement it and you do it anyway. I'm not a huge fan of that. I'm more of a fan of have the hard discussions up front and figure out how you can help change perspective if you can, right? So that was what we tried to do, and in the end, what ended up happening is we implemented the way the customer wanted, and then it broke everything. And then the customer came back and said, hey, we need to, I'm realizing this is actually not working, so.
What if you do what the customer wants and it breaks,
Yep.
but then they blame it on you? The ideal customer, right?
Yeah, right? This is the perfect customer. I hate to say it, but document as much as you can, and also don't hide things. Like be upfront with everything, right? Cost, change to cost, change orders. If you're doing a change process in your design, make sure you're upfront about everything. This is really communication is the name of the game, and then document it. Show the trail of how we got to a decision. That really goes a long way with building trust.
I wasn't planning on asking this question, but how does one document?
Yeah, good question. So, it really depends. It's going to depend on where you're at in your process, where you're at in your career, and where your customer's at. Really, honestly, it can be something as simple as we had a conversation. That's good, but document what was taken from the conversation. It can be written up in a Word document. It can be written up in a notepad. Like it really doesn't matter. But send it to the customer, so you both have documentation. And as soon after something happens, and then if it's just a conversation, for example, or do it while you're actually having the conversation, right? Take the notes and then provide it to them so they have a copy of it, right? I mean, there's a whole reason we have the carbon copies on paper, right? It's so people can have copies of that. But it's the same idea. Just document it, write it down, make sure the customer has a copy, you have a copy, and then show where decisions are being made. I think that's also, this is kind of a side tangent, but I think defining what decisions were made and why is a really good thing, right? Understand why we made a certain design decision. We needed to come to some sort of design decision. This is what was decided. This is why it was decided.
So is there a certain person on the team that's assigned this documentation role, or does everyone on the team do their own documentation and they're merged all together? How does that work?
Yeah, so I think that's going to be really dependent on the company you're in or where you're at. If you're like an independent contractor, you're responsible for everything, right? But if you're working as part of a team, understand that. Figure out who it is. Maybe it's a project manager. Maybe it's the project lead. It could be an individual engineer, right? It really depends. I would say whoever is involved. So this is my philosophy: is whoever's involved in the conversation, everyone has a shared responsibility in that, right? And I would throw the customer into that too, right? The customer has just as much responsibility to document and understand what's happening and why, as the people doing it, right? As the engineers. So I don't think it matters who does it, as long as somebody does it, and then everybody that's involved in it or that needs to be involved in it understands that's what happened.
That's wonderful. That's a great tip that we weren't planning on discussing. So
Yeah.
good conversations take a natural flow, and that's where it led us.
That's right.
So we were past the green and
right.
define. We're talking about ideate now, right?
That's right.
The yellow.
Yeah, so ideation, really this comes in a lot of forms. This is the part that I think a lot of people have fun with, right? This is the back of the napkin sketches. This is the, I built, I wouldn't even say building yet, right? Prototyping is where you get to building. But in ideation, it's really just throw an idea out there and see what sticks. These ideas can be in your mind. They can be sketches. They can be whiteboard drafts. They can be a lot of things.
But don't you have a hypothesis before you throw the idea out, or that's more the prototype stage?
For sure. No, I would say that you definitely have hypothesis, but I would say that kind of goes back to the green part here where it says define. That's really where you're taking through and saying, this is my hypothesis. This is what I want to prove true, and that's what I'm going to define, right? And so now, what do I need to do to prove that true, right? So in ideation, it's going to be, hey, you know what? I believe that this, here's an example. We'll use this fixture that we've been talking about. I believe that smooth jaws are going to actually clamp better than serrated jaws, right? That's the hypothesis. So how do I go prove that true? Well, I need something that's smooth to prove it, right? So the idea is I'm going to build or design smooth jaws or I'm going to build and design, or here's another idea. I'm not going to design it. I'm going to go find something that has smooth jaws already, like a vise or something else. I'm just going to test that, right? So these last three, ideate, prototype, and test, the red or the yellow, orange, and red, really those, I would say you can flow through those very quickly.
Let me ask you about that. So the device, the smooth surface, but there are several factors that take a play, which is what about the material that the surface is made of?
Yeah,
right?
Absolutely. So it's important to understand that. So in this particular case, I won't share the materials that we're using here, but we knew that this was going to be a metal on metal contact, and the type of material was going to be important, right? We knew the material properties of the samples. So we knew hardness, we knew Young's modulus, we knew all the different things that we should expect from that material. So in this particular case, if we knew those, we either needed, what we needed to test really was what happens if the material is softer, right? Even if it's a metal, like for example, if this is, if the metal is some sort of a steel versus aluminum is softer, right? So if you're using steel and aluminum and one gives, which one gives first? Probably the aluminum because it's softer, right?
Perfect.
That's an example of that. So we would look at those different materials, and yeah, we would need to consider those as part of this.
All right. So you said that the last three you can flow through them. That makes sense. You had something that you wanted to talk about. There was wicked problems.
There's this great story that's given. You can go check it out somewhere. Search about wicked problems and computer mouse. Okay, you can find out about that. But the idea of a wicked problem, it is literally a technical term, right? Wicked problem. Sounds like you're from like the East Coast, right? Oh, that's wicked, man. You know?
Give it a thumbs up if you've ever heard of the term wicked problem before.
That's right.
I haven't yet, so let me know.
Wicked problem is a technical term in design thinking. And the idea of a wicked problem is essentially there's not really a right solution out there. Another way that I've heard it described once before was you can't really analyze your way to a solution. You have to, you literally don't know what the solution should be. So instead you build your way through to a solution, right? Using the example of the computer mouse, how do we arrive on the design of the computer mouse? And you know, I'm paraphrasing this heavily, but the idea was you'll know the answer when you see it, right? So in this case, what we don't know or what we can't analyze our way to, you literally have to build your way through, right? So in this particular fixture that we're talking about, one of the things that we didn't know about or we didn't understand was how do we know there's enough force on the wire to make it work, and what angle should that force be applied at, right? There's a couple different things. We can dig into that a little bit if you want to unpack it.
How do we know if there's enough force on the wire produced by the clamp?
That's right.
Well, it has to be enough force to constrain it, but not so much that it breaks it.
That's right.
So how do you find that sweet spot?
Yeah, so there was a lot of math that we went into this, but let me just kind of share an example here. So
let's geek out. I want to see the math.
Want to geek out?
Just kidding.
So let me just explain a couple things that's going on here. I'm gonna as we dig into this, I kind of want to let me change the transparency on some of these parts here. Okay, so when you're looking at these parts, essentially these are just guides. The most of the force, you'll notice a couple things. I've got springs that are up here attached to this dowel pin, right, with slots on it. And then I've got a spring, a large compression spring right here. You'll notice, if you're observant, that the force path, so this one is a compression spring, which means if I compress it, the force is acting in the downward direction, right? These are extension springs, which means they are acting, there's an X and a Y component, which is acting opposite of that, right? And what we also notice is that this is on a cant, this is slanted, right? So the way the math all works out is in order to get these jaws to move directly left and right, what we have to do is we have to essentially hold what I'm going to call the piston, right, which is this blue part I'm highlighting right now. You have to hold that stationary, and everything else has to move around it, right? So what happens is you have this clamp body, which is the actual part that moves. And when that moves up or down, and of course it's not going to slide in this, but if we were to change the display state here, so for example, if I go to close, what's actually happening is the clamp body is using this main compression spring force to push it up, right? So this right here is the main force driver, right? The other thing is, because of that, This ball actually goes onto a hanger that the customer site for a quick in and out, right? So this was already defined. This was a constraint for us. We needed to mate up with what they already had. So in this particular case, this entire section right here that I'm highlighting blue, all of that is relative stationary, right? So it's stationary relative to everything else. But what you'll notice is that this clamp then takes the brunt of the force transfer, right? So this is hanging here. The spring is pushing down, so you've got we'll call it in this case a Y component to your force vector, right? And this spring has to be stronger than the tensile force that you're pulling, if that makes sense, right? So the wire being down here at the bottom, which I'll show in just, I won't show the wire, but showing down here, this is where it clamps, the wire being pulled down, so everything's along that axis. And what's happening is, as long as I do not exceed the amount of force that it takes to compress this spring, then the wire will stay clamped, right? At any point, if I overcome that force, the wire potentially could come unclamped.
So how did you calculate the forces?
A lot of math. So in this particular case, I mean, you think about a typical compression spring is just F is equal to K times X, right? So you've got your K factor, or your K, not K factor, the K value for a spring. That's like a constant or a ratio, right? And then you've got the X, which is the displacement. So in this particular case, the force was equal to my displacement times whatever the value I get directly from the manufacturer for the spring, right? And so I can calculate forces there, and I can know that at certain displacements, I needed to have some sort of value, right? The other thing I knew is I knew what the requirement was for the tensile, like what the max force the wire would see. I knew what force that should be, and so we added a safety factor. We said, okay, if it's going to be, I'm just going to throw a number out here. If it's going to be 5 pounds or something like that, I know I need to have some sort of safety above that. It needs to be able to hold more than 5 pounds, because at 5 pounds, it's going to start slipping, right? So in that particular case, that was fairly straightforward. Where it becomes more complicated is I'm also adding some force from these springs, right? So these springs are also pushing back on this spring in a X or Y component, right?
So one thing about these springs, imagine that they're connected to the dial pin. The CAD is not showing that.
That's correct. And that's one of the challenges of CAD, right? Is we have these solid bodies. This is a very dynamic system, right? So in some cases, talking about the wicked problem, I can model this stuff up all day, but at some point I need to physically be able to get this on, put the springs on, test everything, and make sure it's doing what I think it's going to do.
So at what stage did you say, you know what, I'm ready to test this prototype?
Yeah, good question. So we tried to prototype as early and often as we could along this, right? So there were different phases, different places. So like, for example, I talked about the smooth jaws, right? We wanted to test that. So we found a way to test that without even having the clamp. We just tested on different materials, different surface roughness, basically, and found that, okay, this is the jaw face that we want to use, right? This kind. Eventually, I mean, really, at the end of the day, it wasn't until we built everything. This was a difficult assembly where we really, and it's not really that complex, like it's a pretty simple mechanism. So we actually needed to build the entire thing and assemble it before we could test it. And once we tested it, there's something I'll mention about this. We knew we weren't going to have time or budget to really go make a lot of changes. So for example, this particular part right here may seem like a pretty simple part, but it also has a really special coating that has a really long lead time, so it would have a low friction to it and withstand the environment it was going to be used in. So we knew, because of that, we wanted to build in as much, what's the word I'm looking for? Like adaptability. I needed to be able to dial this in without having to make significant structural changes, right?
Wow, look at that constraint.
Yeah. So what we knew is, once again, going back to the spring, right? This is the main workhorse of the entire fixture, this blue spring I'm highlighting right now. What I also know is force is equal to K times X, right? So increase the force, I have to decrease, or in this case, increase the displacement, which means I have to constrain the spring more. So a very simple but effective way to do that is we literally just added shims. We added like spacers, different sizes.
Want to zoom in a little bit more where the shims will be?
Yeah, so those are kind of hard. I think we actually have them in the model, but you can see here, you can see up here against this surface, I can actually literally add a shim right up into that surface area.
But don't you have to disassemble the entire fixture to add the shim?
Correct. You have to disassemble the clamp, right? Yeah, you would have to disassemble the clamp. But what I know at certain ranges what force I should expect, right? So by compressing the spring more, I'm actually, I'll call it a preload, right? I'm essentially adding preload to the spring so that at certain displacements, I'm able to get that. Now, you're right, I have to disassemble it, but I made this so we could disassemble it because at some point springs will wear out, right? Or we might need to, depending on the wire samples that they're using, we might need to actually increase or decrease the amount of force here, right? So the way to do it is build it so we could disassemble it and make it so we could actually dial this in using off-the-shelf parts.
What's something else that you'd like to mention about wicked problems?
So something else I'll say with this is it's right up to that point. We didn't know the solution until we actually found it, right? So it's kind of one of those where I'll use the jaw face as an example. We tried multiple different ones, but it was really difficult to the size of the wire, the forces involved, the different things that were going on. We knew, well, let me put it this way. The customer had an issue with the wire slipping during testing. And they also had an issue where the operator needed to unclamp it, but we're talking hundreds of pounds of force to unclamp it. They were literally using a lever bar and like a hammer to open the clamp, right? It was just too much. And so, one of the constraints was we need to get this down below like 3 pounds of force from the operator. The operator needs to exert no more than 3 pounds of force to open this clamp. But we still need to solve, how do we clamp the wire? And you're telling me right now you're using 100 pounds of force to open the clamp, and you're still having issues with slipping. So what's causing that, right? I'm sure there's a way we could analyze our way to it. Maybe there is. I wasn't at that point, right? The amount of texturing and different things that we needed it just doesn't make sense to do. So in this particular case, we built our way through it. We wanted to be able to find a way to say, these are the different things, let's try that. Let's try this. Let's see what solution works best, right? And once we found the solution, that was it. We just tried the different things. It was more like a trial and error, and then we found it. One other thing I'll mention about wicked problems is you'll find there are other projects I've worked on where there's not really a solution that exists. This is a little bit, maybe not a great example of a wicked problem, this particular clamp and fixture, but there are going to be times where you're going to come across stuff, especially if you work in research and development, which is where a lot of my career has been. You're going to come across problems where there is not an answer. Like there's not really a right answer. And finding ways to test it, build it, test it out on people, test it out on your customers, whatever it is a huge deal, right? You just have to find a way to build your way through it, figure out if it works, find what doesn't work, and really that's my 2 cents on it.
This will be the last question about SOLIDWORKS, and then we're going to talk about what Tanner does at home for his mechanical engineering with his family. So what modeling technique do you use to design this mechanism, and why did you choose that method? We got like top-down modeling, as many of you are familiar with, master part modeling. So what do you do? Because designing motion in SOLIDWORKS is sometimes not the easiest thing. Yeah. So how do you do that?
Yeah, so I mentioned a lot of math on this one. So there was a lot of angles I needed to figure out, right? Like for example, if we're looking at this particular fixture, why is this angle where it is, right? Why do we have it like that? Why do I have angles up here? What does that all matter? To be honest, I tend to think in terms of sketch layouts, right? Like I tend to think of a flat sketch, a 2D sketch, and extrusions, right? Or a flat part and then it gets folded up, right? That's just kind of how my mind works. So I prefer that method, but I often will take different parts to this and I'll actually, like for example, on this assembly, I may actually go in here and then I would add a sketch over this somewhere and say, okay, what do I need to know? And so, like for example, I might select here on, let's just choose the front plane, right? So I would actually go in here and I would literally sketch something and I would say, okay, I need to know where a certain part is relative to another. So I might actually just like come in here, sketch this out and say, okay, I know that if this is up this direction, you can also use the evaluate tools, if you're measuring something, but like if you're just trying to figure out like how things are going to interact, it's a really, for me, it's a very simple way to just come on here and say, okay, what constraints do I need to apply to this? I want to make it a horizontal. And then this one, I want to see what happens if I increase. If I know that angle is at 75 degrees, which it is, if I want to increase that angle, how is it going to change my geometry? And is it going to impact any other constraints? So I like to work from a sketch perspective, think about the constraints physically, and then build up from there. I know there's a lot of ways to do it, but
So I've seen on YouTube that some people do layout sketches and they give the motion to a layout sketch.
Yeah.
Is that the method you utilize or no?
you know, I wouldn't say quite like that. No, I'm more looking at it and saying, okay, this is I'm just going to do a sketch of a part, and then once I get into the assembly context, I'll add mates, right? And then I'll add. In this case, this isn't something I wanted to get too technical with the mates and how I needed to look at it. I mean, you can do cam mates, you can do all sorts of stuff. In this particular case, it was really simple standard mates, right? But yeah, individual parts and then build up from there.
Perfect. Well, we saved the best for last. So Tanner is not only a mechanical engineer during the day. When he goes home, he likes to teach his kids mechanical engineering, and also, if I understand correctly, work on just different hobbies that involve mechanical engineering. So Tanner's going to pull up a video on YouTube. Many mechanical engineers watching this know that it's a passion, and you not only do it in the workplace, but you also do it at home. So Tanner is going to show us a little project that he did at home for his family. So why don't you show us the big picture of what it was?
Sure. So this is just one of the many projects, but we had an old Power Wheels, one of the ride-on Jeeps, and my kids, I got two little boys. They loved this thing, but the batteries that came with it were just, I mean, it was old. They were running out, and it just wasn't worth it to me. So I ended up coming in here and I ended up doing just a whole rehaul or overhaul on the electrical system, right? So this wasn't as much mechanical design, but I'll talk about that in a sec. But yeah, in this particular case, I went ahead and just did a revamp of the electrical system, changed out the battery system, connected it all in, made it so it was a lot easier and more fun for my kids to drive. So it goes faster now, has a little bit more torque.
If you want to scroll down and show us that you were like diving in, getting your hands dirty.
Sure. So I'll just kind of, let me get through here. So you can see these are like some of the parts I used using, but really this is what I was doing, just pulling stuff out, ripping it apart, putting it back together. And then of course, like anything, you've got to test it, and it wouldn't be complete without a test drive myself, right? But it was a lot of fun. We were able to take it and just take it for a spin. So
this video has 11,000 views. It's not bad.
Yeah.
Almost 12,000.
That's right.
Right on. Well, if you want to watch the full video, we're going to have a link to that video in the description below. Feel free to follow Tanner, subscribe to him on YouTube, and the link to his LinkedIn will also be down below. And so will mine. If you want to learn and watch more episodes about mechanisms and mentorship, you can find the link to my LinkedIn where I post all this content below. And any last words for any mechanical engineers, maybe in school, early on in their careers, any advice for them?
Thanks, Rafa. Appreciate it. The only thing I would advise people to do is just get your hands in there, start working on it, try stuff out. I think that's what got me to where I'm at, right? The projects I do at home, it's because I enjoy them, right? So if you really have a passion for it, you'll find ways to just test it out. Find a way to just try something, learn as you go, and have fun with it. Don't stress out about it too much. There's always needs for good engineers, so this is a great place to start.
Tanner Green, Rafael Testai. Until next time.